Professor Srikanth will help us understand how sustainability terminology is often misapplied, how selective data or unverified claims can create misleading environmental impressions, and why responsible, transparent communication is as crucial as the responsible engineering. His insights will be invaluable not only for researchers but also for educators, policymakers, and industry professionals striving toward genuine sustainability. We are extremely honored to have him with us today. Please join me in warmly welcoming Professor VVS Srikanth.
Thank you, Dr. Bhargavi, for the kind introduction. Let me switch on the camera for some time. Is it necessary that I should keep my camera on throughout?
Not a problem, sir. You
Not
can
a
switch off
problem.
because network
Okay.
issues will be slow, right? Yeah, you can
Yeah.
complete.
So, anyways, yeah, thank you so much. I thank also Professor Swami Naidu for inviting me to participate in this FDP and also Dr. Bhargavi. This FDP, I'm sure, is will be very beneficial for the participants, and it is a well thought of program on hydrogen energy pathways to a sustainable and decarbonized future. The premise of my presentation, as Dr. Bhargavi mentioned, is to alert whoever wants to or wishes to work in the area of energy, or especially hydrogen energy, which is buzzing these days. To be is to alert them to be careful in using the terminology and not to make misleading claims or misleading statements. This is very important because these days it has become very quite common to unmindfully use the words green and sustainability without any. Now the question is it appropriate? Is it even ethical to claim a process or a method or a methodology or a technology to be green and sustainable without quantifying appropriate uh, descriptors? The answer is absolutely no. Unfortunately, most of us, as I said, loosely use these words and forget about quantification. We don't even describe the descriptors to claim something to be green and sustainable. So this is the motivation. So while take examples with which you can, I hope most of you can connect. And my presentation is not expert presentation, or it is rudimentary in kind, which has simple definitions, and where we as academicians or researchers falter the terminologies, and without the problems which we can face if we don't quantify the descriptors. Some examples I'll take and then try to put forward my point of view on the so-called green technologies or green hydrogen energy or anything of that sort, and something called sustainability and sustainable energy technologies, and so on and so forth. Um, I Are you able to see my presentation? Not, no, right? Okay, let me share my. I'm sharing, but yeah, let me put it on a full screen. As you can see, the title is green washing, and I'm using a paintbrush to represent what is washing. It implies that something is not green, but you're painting it green, something like that. And obfuscation is nothing but obscuring things for the public. We claim that something is sustainable, but we don't give all the details about what we are speaking. That is, in other words, obscuring the real sustainability aspects related to whatever you do. It could be a process, it could be a method, it could be a methodology, it could be a procedure, it could be technology, it could be as simple as a simple research that you project wise you do in on a day-to-day basis in your laboratory. Um, so for that, it is important. Let me just a minute. Let me switch off my camera. Yeah. Okay. With what ideally is a green technology. Any technology with ideally any technology with zero detrimental environmental impact. That means any technology you developed has actually is not harming the environment. Environment includes humans, animals, plants, water, and other any other aspects of environment. So ideally this is the case. Okay, but how deviated we are from this basic ideal definition of green technology. Now, I'll pose a question to all of you. Now, you can see a big building with an array of large array of solar panels. This is actually the largest building in University of Hyderabad, School of Life Sciences. On the top of the building, they have put a lot of solar panels in order to convert solar energy into electrical energy, and this is solar energy conversion. Now the question is this solar energy conversion technology, is it green, is it clean, or is it renewable energy conversion technology? So unless we have a clarity on the definition of what is green, what is clean, and what is renewable, uh, we changeably, and that's actually not acceptable. We'll come back to this. You may have your answers, I mean, with you. Later on, I'll again ask what would you name this technology as after a few minutes of discussion on this. Okay. Now, if you see such a scenario, this is a cartoon I copied from the internet, and the source is given there. There is a man who is actually painting these chimneys, which are actually releasing gases, and you can connect with this image very easily. These gases emitted by the chimneys, emitted through the chimneys, is not good for the environment. But this man, in order to show that this is green, is painting a green color on the chimneys. So what is green washing? It is making exaggerated or misleading claims about the green in the so-called green technologies. So I elaborate this, what I mean by this with the same example. Now, giving some numbers, these solar panels can actually convert solar energy to electrical energy amounting to 1100 kilowatt peak power. And then these panels are supposed to be connected to an inverter so that the DC is converted to AC and we can use. With this setup, it is expected that 1.6 million units of electricity, that is the solar energy, is converted into electrical energy. Each unit, you might be knowing, is 1 kilowatt hour. Okay, so 1.6 million units of solar energy is converted into electrical energy, and that accounts to about 1,300 tons of carbon dioxide savings. As far as the numbers are concerned, this is excellent. Basically, you're generating, you're converting one form of the energy, the solar energy, to electrical energy, and most of us know that the solar energy is free for use because it is coming from sun. It is renewable. Everybody can claim that energy. There are no restrictions or reservations. And of course, while converting, because we are converting, and when you make some calculations, the pollution that can otherwise be generated if you don't convert and use 1.6 million units per year through another energy conversion process, not necessarily solar energy. Pollution amounting to 1,300 tons of carbon dioxide can be generated. Okay, so but if you consider the total, the entire life cycle of this technology, which starts from uh, collection of as or the mineral which has the silicon, silica sand, and then processing. So it involves mining, it involves processing, and then once you get metallurgical grade silicon, you need to make solar grade silicon. That also involves processing. Then you need to make bring parts together and make devices. Polishing is there, then device fabrication is there, and then assembly is there, then transport is there, installation is there, then usage is there. And then once the usage is done, maybe this setup will work for if it is properly maintained. That so therefore maintenance is also there. It will work for maybe 10 to 15 years. Okay, after 15 years, after life, what do you do with these panels? What do you do with what all the assembled parts which actually generated 1.6 million all the 10 years or 15 years of their working? Okay, so if you consider the entire life cycle, each step from when you talk about mining, there is pollution. When you talk about processing metallurgical grade silicon from sand, uh, again pollution. When you want to convert the metallurgical grade into solar grade or electronic grade silicon, again pollution. Then assembly, transport, and all involves pollution. Then if the connections are not proper, if you see here, I have a setup which can convert power equivalent to 1100 kilowatt peak, but I have only a 100 kilowatt inverter. That means I cannot convert, even though the panels, silicon panels, are able to convert so much of power, solar to electrical. I cannot actually with this sort of inverter, which is a poor choice. In minimum is 1,000 kilowatt inverter, but here only 100 kilowatt inverter is there. So therefore, the panels may be capable of converting, but the inverters, the choice of inverter, which is made by the ones who are actually have chosen the specifications, have faulted in choosing a wrong inverter. Okay, so thereby, in fact, even though you have all the system in place, the capabilities in place, poor choice of assembly can actually fail the entire thing. So if I use a 100 kilowatt inverter, I may not be generating 1.6 million units per year, because these amount the numbers correspond to the proper utilization, the optimal utilization of the total energy converted from solar energy to electrical energy. So therefore, if I don't my environmental savings or the carbon dioxide equivalent savings will also be poor. Okay. Now, if you consider the entire life cycle, this technology, solar energy conversion technology, is not green. Green because ideally green means at any point of the development of the technology, as assembly of the technology, installation of the technology, maintenance of the technology, usage of the technology, and the end of life of the technology, and the uh, nowhere there should be a detrimental effect on the environment. But unfortunately, in this case, at multiple stages, there is an detrimental environmental impact, and therefore, this is a strong deviation from the definition of the ideal definition of green technology. But unfortunately, you might have noticed that many people unmindfully use solar energy conversion technology or term the solar energy conversion technology as a green energy conversion technology. Okay, so now you see the points in detail. Solar panels can constitute as high as double tonnage of all the global plastic waste. Okay, and I'm not saying this. There are several organizations, non-governmental and governmental throughout the world, which actually calculate very carefully about everything that goes into the technology. Okay, so in fact, solar panels can constitute double that of the plastic waste. Okay, so therefore there is a strong carbon footprint, and the fossil fuel energy, that is used in preparing these solar panels, mining, processing, fabricating, making single crystal silicon, polishing, fabricating, assembly. So, okay, there are so many processes involved, manufacturing processes involved. It involves raw materials have to be made, transported, processed, subsystems, assembly, and so on. Now, if you see the energy spent on these processes, it is actually corresponds to about the fossil fuel energy. Lot of fossil fuel energy is expanded. Okay, and in numbers, 45 grams equivalent carbon dioxide equivalent per kilowatt hour. So, if I am converting 1 kilowatt hour of solar energy to electrical energy, that corresponds to greenhouse gas carbon dioxide as 45 grams, which is not ideally good for the environment. Okay, and you see a lot of toxic chemicals, acids, especially concentrated HF, and other elements like lead, cadmium, arsenic. Without them, these panels are not there. They don't work basically. And what about the wasted solar panels at the end of the life? And it is anticipated, it is expected that 80 million metric tons, million 80, million is 10 power 6, metric is 1000 and tons by 2050. Okay, so what will you do with those wasted solar panels? Okay, so these actually, because if you don't consider them, you can blindly say that this is a green technology, because if you obscure all these, and I'm only interested to speak about converting solar energy to electrical energy, but I'm not bothered about all of these, then that's the obfuscation. That is obscuring the details, the complete details about what you're doing or what others are doing. Now, let us see the definitions, okay, of because people are using clean, renewable, and green, they must be different. Okay, so what is clean energy? It is energy when expended, that means when you spend, produces minimal greenhouse gas emissions. So in the case of solar energy conversion to electrical energy, the greenhouse gas emissions are very minimal. So therefore, that energy, what is that energy? Solar energy can be called as clean energy. Then what is renewable energy? It is the energy converted from a renewable source. No, the first one is a clean energy expended. So if you expend the energy that you convert from solar energy to electrical energy and use that electrical energy, the greenhouse gas emissions are less. So therefore, you can tag clean energy to solar energy. You can also tag renewable energy to solar energy, because it is energy converted from a renewable source, because solar sun is a renewable source, or the energy that is tapped from sun is a solar energy. It is energy converted from one form to the other. So in this case, solar energy to electrical energy, no problem. Or energy expended without ideally harming the environment. That's the ideal definition of green energy. But unfortunately, in the example we have taken, the solar energy conversion, if you take the complete life cycle, there are several stages in which there is a lot of pollution that is generated, and unfortunately, whoever is bringing out this technology doesn't talk about these lacunae, these gaps, and they don't quantify, they don't talk, because if they talk, many people may not use the technology. So what these definitions tell? These definitions tell us that the clean and renewable energies need not always be green. Okay. Now, is there any example in the world which we can cite that can fall in the category of ideal green energy technology? Now, we'll come to that, but now coming back to this, having noted these definitions, having noted what would you call this technology as? Would you call it as clean energy conversion technology? Would you call it as renewable or green energy conversion technology? Okay, I would basically say that renewable energy conversion is involved, and it is some sort of a clean energy conversion, because the emissions involved when we use electrical energy, because the total emissions, okay, when you consider the total life cycle, are far less than any other fossil fuel energy conversion technology. But coming back to the, is there any technology ideally following the definition of green technology? Probably the only example is the natural photosynthesis. Here, again, renewable source, clean, that is converted into chemical energy. Most of you might be knowing. Okay, this is probably the only example one can think of which aligns with the ideal green energy definition. Here, actually, in fact, it is not harming. This process called photosynthesis is basically not harming the environment. In fact, it is helping the environment the other way around. Okay, so if we go back to the technology definition, ideally zero detrimental effect, and this probably is the only example one can cite, even though we don't treat this as a technology, because technology means it has to be from humans. Okay, but nature has given this, nature has decided this technology, and it has been running throughout from the time of evolution, and at no point in time somebody told the photosynthesis or the nature, please stop for a while because you're working too much and for too many years. Okay, it's a continuous process. It has been continuing, it will continue, and it will do the job decided by the such a sustainable technology too, because it has been sustained over so many millions of years. Okay, so whenever there is a human intervention, in the name, humans are always curiosity driven, and they also want they always want to have a comfortable life. Okay, in the name of comforts, in the name of development, humans have interfered too much with the nature, and developed several technologies, but unfortunately they have not taken care of the environment, and now we are in problems because environment has deteriorated so much. Land, soil, air, water, so many things have been polluted because of the continuous wants of humans. So whenever there is a human intervention, of aligning with the ideal green energy definition is zero. Ideally, it is impossible. Whenever there is a human intervention, ideally there cannot be any technology which can be termed as green energy technology. Now, but we need some acceptable definitions, because we are humans. We always compromise. We have a compromise formula. We still want to do research. We want to publish. We want to have paid. We want to have families. We want to have cars. We want to have money. We want to be comfortable by whatever means. So what we do, we compromise, and we take an acceptable definition. So if we think in those lines, yes, please. I think somebody is online. Yeah. So if we take a compromise formula, any technology that enables harnessing energy with minimal environmental impact, as the definition the compromise formula gives to many researchers and academicians or technocrats who want to work in the area of green energy conversion technology. Now, if you see the United Nations, even United Nations has not used the terminology green energy. Instead, it has used clean energy. Lot of effort, lot of research has gone in naming the Sustainable Development Goal 7. They named it as affordable and clean energy, not green energy. Okay, because ideally, whenever there is a human intervention, at the most it can be clean energy where the environmental emissions are there, the carbon emissions are there when the energy is used by the humans, but it can never be clean green ideally. But of course, as I said, we compromise and we use a compromise formula. Okay, now uh, any technology you are replacing, basically any technology with zero negative or detrimental environmental impact to any technology with minimal environmental impact can be considered as a green technology. Sustainability. This again, sustainability is an aspect that was introduced by the UN to the member countries of the United Nations. And in 1986, there is a commission called Brundtland Commission, which was entrusted with this work of looking into the environment and the living aspects of the humans and the other creatures in the environment, water, land, all that. They came up with a definition for sustainability. The Brundtland Commission is meeting the needs of the present. Of course, we are in the present, so we need to meet our needs. So, what is sustainability? Meeting the needs of the present without compromising the ability of future generation to meet their needs. So, future generations will also have needs. For them, we should not, for our needs, we should not compromise with the nature in such a way that the future generation lose their ability to meet. And what this commission said in their report, which is still valid in spirit and also in practice, is that this particular aspect called sustainability should be built on 3 E's network. Okay, framework. 3 E's framework. The 3 E's are environment. Of course, most of us know that it is related to environment, but it is also related to the economy and equity. Okay, environment is as important as economy of or a country, and the equity, how many people a particular technology is reaching. Okay, so there we'll take examples to understand it further in the coming slides. But nonetheless, what this commission has told, and all the member countries of the United Nations have agreed to this definition and agreed to establish the sustainable development goals. And all of these goals, which are listed on the website of United Nations, are built on the 3 E's framework: environment. It is not just environment, it is not just economy, it is not just equity. There should be a balance, an optimal balance between among the three: environment, economy, and equity. You cannot say I'll only work for the environment and let go equity and economy, and the other way around. You cannot say I will only talk about equity but I don't consider environment and economy. That also is not that. Any process or any methodology, procedure, technology, if there is no balance between among that process, the technology cannot be called as sustainable. As simple as that. Now, what is this environment, equity, and economy? Okay, environment, as most of us know, it is about the protection of the environment. It can be water, soil, air, other microbiome in the soil, other microorganisms in the soil, water animals, land animals, plants, trees, all that comes under the purview of environment. We should it continues to thrive even for the future generations. It has to be good for us. It also has to be good for the future generations. Okay. Now, what is economy? Economy is the too easy to understand easily. If a society is economically strong, implies their living standards are pretty good. Okay, living standards are pretty good. They have enough resources. They have resources. They have excellent resources in the quality wise. Resources can be any resources, natural resources or other resources, okay, through which they can actually trade with the neighboring societies or neighboring countries. That's the economy. Now, equity, as I said, is equally important. Environment, economy, and equity. Equity is uh, uh, any technology or any process, is it reaching to many of the people in the world? For example, a technology is, let's say, India. Uh, is it reaching? Is India only talking about economy, improving its economy and environment, and not allowing this technology reaching some poor countries or people in poor countries? For example, vaccinations, for example, is one aspect. Okay, when a vaccination is developed ethically and morally, this vaccination is for protecting everyone. For example, in the case of COVID, nobody thought about economy. Nobody thought of making profits. Okay, there is emergency, a human emergency. Humans had to protect humans, and for that, at different places, vaccinations were developed, and they were made available affordably, and in some cases freely, to countries where the pandemic was, could not be controlled. Yeah. So we need to, when we talk about sustainability, somebody is online. Is there any doubt? Okay.
Hello, Srikant sir, please continue, sir. Hello.
Sir, you are noted.
Now am I audible?
Yes, sir, audible, but share the screen, sir.
Yeah, I'll share. I'll share. Yeah.
Uh,
Yeah. I hope I was not muted from the beginning. I didn't check.
So everything is fine.
Yeah. Anyways, let me continue. Okay. So even if you are considering a lab experiment, there are sustainability aspects or aspect related to how to conduct an experiment, considering environment, economy, and unfortunately, at the most, we will only consider about environment. We claim that we have used some reagents, and then we claim that our process is sustainable and green. We'll see with some examples how bad such a claim can be. Okay, so yeah. Now, when it comes to technology, what is sustainable technology? It is to design, develop, and implement engineering solutions that meet present needs. So I'm extending the definition. We humans we want to meet our present needs. But when it comes to technology, it is related to the engineering for us or for animals, for whatever technology that takes on this planet Earth, to meet the present needs without compromising the ability of the future generations. Okay. Now, the problem here is when we talk about engineering solution, it has to be, the moment you talk about engineering, it has to be design directed. Okay. Unfortunately, none of us, I don't know, maybe I'm exaggerating. Maybe some of you follow that, but most of us, I would say, would not have even design of experiments for whatever we are doing. Okay, forget about fundamental design parameters or the primary design parameters, secondary design parameters, tertiary design parameters. We don't consider them. We only catch the buzzwords, do some substandard literature review, and we say we find gaps, and then we say we are conducting. And if you are lucky enough, you end up with the patent. The work inside maybe of poor quality, but you can still end up getting a patent or an excellent publication in a very big journal. But the quality of the work inside can be still poor. Okay, but we still claim that it is sustainable or whatever. Okay, so now. Now, in any technology, when we say technology, engineering is involved, and when we say engineering is involved, science is also involved. Okay, engineering is built on science, and science is built on engineering. They have to, each one helps the humans and the planet to go. Okay, so when we talk about engineering solutions, you should integrate these three: environment, economy, and equity, such that the engineering solution ensures a long-term viability, at the same time minimal environmental impact. Okay, so this is applicable not necessarily only to technology. Whatever you do, you can attach or align or tag this definition of sustainability to that. Okay, but whatever be it, you need to consider environment, economy, and equity. We'll see one by one what it means. Okay, now when we talk about a technology, to term a technology as sustainable technology, what it means environment wise. Okay, when we say engineering solution or technology, it should involve efficient resource utilization, and this is possible only if you design your experiments. You have a design of experiments, and only if your experimentation or your engineering is based on the primary design parameters or secondary design parameters or appropriate design parameters. What are resources? Resources is water, energy, and of course materials. Okay, without materials, nothing, no technology gets developed. Okay, even the software technology, even the computer technology needs materials, because only through materials you either read, calculate, store, or read the data. Okay, and then environment also implies minimizing waste. If your solution is in such a way that the waste generated from that process is minimal, okay, that constitutes environmental E in the sustainable technology. Reducing carbon footprint, of course, this is also linked to the minimizing waste, and of course, greenhouse gas emissions as low as possible. So, and then promoting renewable energy sources like, for example, solar energy. For everything for everything you do, you use renewable energy, not the fossil fuel energy. And of course, choosing eco-friendly something called green manufacturing, which is, as I said, ideally it is impossible, but otherwise with the acceptable definitions, one can actually do green manufacturing. So all of these points constitute the environmental E. The E, one of the E's is environment. So if I am talking about sustainable technology, I need to quantify all of these. I need to have numbers. If I am saying that I am bringing out a technology, what is the resource utilization in that? Okay, is it good? Is it bad? Is it okay? Something like that. What is the waste you generated? Is it hazardous? Is it good? Is it biodegradable waste? And then carbon footprint you have generated in, even this is applicable to even for a simple experiment in the lab. Okay, so we in fact safety is one aspect which we fail often in the laboratories. We don't train the students to follow the safety measures, and therefore we are contributing to the carbon. It's not about the safety of the humans, it is the environment, and we are a part of the environment. Okay, so something like that. And what constitutes economy? Okay, if I am saying that I am bringing out a sustainable technology, with that technology, will the economy become stronger? Will the society, if let's say the technology is bought by NIT, is it good for Raipur? Is it good for Durg district? Is it good for Chhattisgarh? Is it good for India? So on and so forth. Okay, will the people in these localities become stronger? Do they have more spending power? Will the quality of life is improving? Is better with this? Will be better with this technology? Something like that. And it also implies economy also implies cost with long-term benefits. Okay, if I am developing something, it doesn't become redundant in a quick time. Okay, it will last for a long time, and there are theories which say that a technology which lasts for a long time, is very good for the environment, very good for everybody in the environment, and especially the humans. Okay, for example, you take water. Okay, now we humans we need water. Is there any at any point of time humans have deviated from not taking water and they've relied on any other solution or any other liquid in their human race from the time of early humans, or from the time the water started the humans started drinking water? Okay, so that's, then we say it's sustainable, right? So many millions of years water is there, and we'll continue to have water. There is no replacement for water on this planet. Okay, now any technologies which correspond to such a help to the humans or animals, where there are that is linked to the economy E of that particular sustainable technology. Okay, and then economy also implies energy efficient and low maintenance solutions. Okay, energy efficient because you will be spending less money to develop the technology, and low maintenance because you don't need to spend much on maintaining the technology. Okay, we have discussed this energy efficient fabrication, for example, of the solar panels. Okay, why the panels are so costly? In fact, they should not be so costly because it is available in the nature, right? But because the processing is not so energy efficient, they're still costly. Okay, so something like that. And of course, once the panels are made, you have to see that the surface of the solar panel is clean. Okay, otherwise they actually mask the surfaces, mask the solar light to enter the active area. And then if the light doesn't enter the active area, there are no electrons and photons, protons generated. Okay, the positive and the negative charges generated, and therefore there is no electrons and holes. I said protons, I'm sorry, generated. So there is no electricity basically. Okay, so if you when you say I am developing a technology, it has to economy wise, it should attract only low maintenance amounts, and not much money should be spent on maintaining it. Okay, and of course circular economy principles have to be considered. The RRR technologies, for example, reuse, reduce, recycling, repurposing, and you can increase that R. It is left to us. We have autonomy to put any R term there, and these principles have to be included while developing a technology. Then it is linked to the economy. Okay, so you will not spend much. You will when you say I am using the principles of circular economy, where I am repurposing a particular product has come to its life cycle, it end of life, but I am repurposing it. I am using it for something else. The amount of the burden on the society will be less economically. Okay, so all go into the development of the technology called sustainable technology. Then we say the economy is being balanced. Okay, economy is being balanced, and of course any technology, in order to call it a sustainable technology, life cycle assessment. In fact, in the engineering, especially chemical engineering, this is a part and parcel of their education actually. But unfortunately, when it comes to the practice, very few industries or very few do the life cycle assessment. Okay, it is not just the environment, it is for cost. We need to do also for the cost, because it is related to the we are talking about the economy aspect of the threes. Okay, so when you want to when you want to claim a technology to be sustainable technology, all of these have to be considered, all of these have to be thoroughly quantified, and then see you're meeting the required bench. Then you say economy wise, I am also satisfying this. Okay, environment you need to do separately, economy you need to do separately, and then with the you have to go to the equity, or either way, any order is fine. Okay, it is not environment first, economy first, and equity later. It can be any order. Okay, let us see what equity says. Okay, now equity says community engagement and stakeholder participation. Okay, this is the first and foremost. What does it mean? It means, are we asking the community, are we asking the constituents of the community? It can be humans, it can be animals, it can be the plants. Do you need the technology that I'm going to develop? So the need analysis is never done. Okay, need analysis, very seldom people do the need analysis. Is the technology I'm going to develop, is there a need for it? Are there people who want to take it? Okay, it starts from the need analysis. Okay, for example, when we are saying green hydrogen, who has decided that we need green hydrogen, whether it is good for the humans, it is good for the animals? Did we ask the community, do you need green hydrogen? Did we ask let's say Indian lithium ion battery technology? It should start from there. So equity starts from actually there. Okay, even the lab experiment, suppose there is a project, you got a project, let's say one of you got a project, or me, I got a project from DBT which involves animal subjects. Okay, then I need to recruit, let's say, a SRF or a JRF or some project staff to conduct experiments on a day-to-day basis. Okay, now what equity means? If that person says, I don't want, even though it is ethical, if I can follow ethical standards and do animal experiments on animal subjects, no problem. But that person says, no, I morally, I don't want to kill animals. I don't want to do experiments with animal subjects. Please change my topic or research or something like that. Okay. A supervisor, as a PI of the project, it is your responsibility to actually consider that request seriously. You cannot say you are recruited for only this project, so you have to do. You cannot force a person. So when it comes to even such scenarios, you need to follow the equity. Okay, so you need to be very careful when it comes to a big thing called sustainable technology, because it has a lot of undertaking. Okay, you need to ensure safety, you need to ensure well-being of the to ensure whoever so you may say, okay, I'll have a cell tower, but cell tower is causing cancer, let's say. I don't know about that, but I'm just trying to bring out an example which actually is something like this. Okay, cell tower is helpful to the people, but at the same time there are cases where there is an apprehension that it can actually cause cancer to the people who are around that cell tower, living around that cell tower. Okay, so so do you say that equity is taken care of in that? Okay, so something like that. So the safety and well-being of the people. Okay, and inclusive and equitable and engineering solutions you should think of. Inclusive means again considering all sections of the people, whether they need it, they want to participate it. Okay, you might have heard about vaccination. Some of the communities in Europe and America, they didn't want the vaccination because it is against their faith. Okay, but can you force them? You say that this is pandemic, you should take the vaccine, it is mandatory. No, that's a violation of equity, violation of human rights. Uh, it is a solution, but you cannot force those solutions because you think that from your side that is the best. But there can be people who probably for whatever reasons, it could be related to religion, it could be related to faith, it could be related to science. For whatever reasons, they say, no, I don't want to include myself in this. But you cannot force in the name of the technology. You cannot say take this vaccine, otherwise or if it is mandatory, you take it. Okay, so something like that. Just for the example sake, I'm bringing out such things so that you can comprehend what. Okay, and ethical considerations, another aspect which most of us, especially in India, don't even consider. Okay, uh, the moment you talk about a technology, if you want to blindly say that I followed I followed ethics in doing whatever I did, best is to follow the design principles. Okay, design directed engineering. By default you will be ethical, you will bring out work. Okay, so otherwise it becomes if you deviate from the design directions, there are chances, there are ample number of chances that you are deviating from the ethics. Okay, especially exploitation of the weaker sections, exploitation of the women, exploitation of the children. I'll bring this aspect when I take the example of lithium ion battery. Okay, ethical considerations even in the lab, in a simple lab, deviate from ethical consideration. Okay, we just want to do research for the sake of doing research, and which is not about doing research, publishing. It is not about patenting. It is not about bringing technology. It is also how we do it. Okay, how we do it is also very important. Is it the correct way of doing? Is it the correct way of engineering? Is it an ethical way of engineering? Is it a moral way of treating people? All such things have to go. Okay, into the development of that so-called technology. And only then we can say if we have strictly followed these in developing the it as a sustainable technology, you are satisfying something called equity. Okay, so all these, all the three, environment, economy, and equity, have to be balanced simultaneously. Okay, you cannot give importance to one and then neglect the other two, or you cannot give importance to two and neglect the other one. It has to be, all the three have to be equally balanced. Now, you see here, I'm showing an the on the left, there is a small boy working with some rocks or some mineral, like some rocks. Okay, now on the right you see there is a globe very nicely with the green color, showing some battery like material, and a leaf representation of greenness. Okay, now if you see, this is about lithium ion battery. This boy is from a country, and he, instead of going to the school, and I'm pretty sure none of us would like our children to work in such at an age of that age, in such mines, mining and sorting and dealing with the pollution directly. Okay, now this boy unfortunately is not going to the school, but is in the mines sorting out some minerals. Okay, now on the right we have something called green technology, green lithium ion battery technology. This, I would say, is making an exaggerated or misleading claims about the sustainability. Okay, because here you see you have violated equity, you have violated environment, you have even violated the economy. Why economy? Because such a boy in Germany or US would not be like this. Why a boy in Congo should be like this? Why a boy in Bolivia should be like this, or a girl in Bolivia should be like this? Why? Why? Because there are only limited number of places where you get these critical materials like lithium, cobalt, nickel, and so on and so forth. And in to mine, you need to exploit the local people. You'll exploit women. You'll exploit children, and the salaries they get are not the global standards, and the amount of money they have to spend on treating their ailments is much more than their earnings. Okay, so therefore the equity is blatantly deviated from. You're violating the equity, and uh, the environment. Why only these countries have to be mined? Because the answer is only they have those minerals. Okay, why don't we develop another technology whereby we don't pollute their country? Okay, and it is like exporting. Pollution to some other country to have a greener country here. Okay, that's absurd. Yeah, that is absolutely absurd, and that doesn't count under this threes framework. Okay, and what about economy? See, economy. Does this boy have enough resources? Is the boy's standard of living is good? No, not at all. And what about equity? If I'm developing the materials mined by this boy, and this material after processing is going into lithium ion battery technology, is the lithium ion battery technology the way it is going to US, it is going to in China, the way it is there in India, is it there in Congo too? Unfortunately. Then why do we call this as still a sustainable technology? Because we are blatantly violating environment. Even violation at some part of the planet is violation. Okay, it's not why. What happens? What if I violate the rights in Bolivia? No, it should not be like that. If it is an engineering solution. Okay, so when we make such exaggerated and misleading claims about sustainability or green, we say it's called as sustainability obfuscation. certain important aspects of it, and highlighting only the aspects and trying to make business. Okay, as simple as that. To make trade, to sell these so-called batteries in the name of green technology, the entire environment will become green. I don't think so. Okay, this is of course you may have your own opinions, but this is what I strongly feel. This accounts for sustainability obfuscation, because this actually obscures the details of what is happening around that technology. Okay, now if you take lithium ion battery technology as a sustainable technology, what we are doing with the environment, we are actually not making any balance among the three: environment, economy, and equity. Environment, some of the countries which have these critical minerals are being exploited. The pollution, the land pollution, air is polluted, water is used, and for example, to mine 1 kilogram of lithium, which probably goes into 10 cars, let's say, okay, 10 EVs, 10 EV cars, okay, just 1 kilogram of lithium, you need 20,000 lakh liters of water. Okay, where do you mine where lithium is there? Where is lithium? Only in handful of countries. And where do you get water from? From their own resource, from resources. So we are, in the name of having lithium ion battery technology elsewhere, we are actually spoiling the environment of countries like Bolivia, Congo locally. So blatantly the environment, so the pollution in Bolivia is pollution on this planet. Okay, it will anyhow diffuse with time into the other countries. And economy, and you see economy, only few countries in the world make lithium ion batteries, and they are rich. And how? They are exploiting other people in other weaker countries and making money. Okay, that's not economy. Economy implies the first and if I am taking Bolivia, the natural resource of Bolivia, if I am mining lithium from Bolivia, Bolivians should be the richest. Okay, not somebody else. Okay, and it comes to equity. Is this technology available to the locals the way it is available to other countries? Absolutely not. So the question is lithium ion battery sustainable technology? I'll leave it for you to answer. Okay, now see the lacunae in lithium ion battery technology. 1 kilogram of battery requires 500 kilograms of various materials. Okay, if you mine 500 kilograms of various materials, you get 1 kilogram of material that can actually be called as a battery material. And if you are talking about a stack of 100 kilowatt hour lithium ion battery manufacturing, it causes about 16,000 kilograms of carbon dioxide emission. Okay, so okay, once a lithium ion battery is made, it is an efficient technology, no doubt. It stores a lot of energy density. It stores a lot of energy, but to manufacture that, you are actually polluting so much of the environment. And what do you do in manufacturing? In in order to get one energy equivalent to 1 liter of fossil fuel, in fact you are spending 300 liters of fossil fuel. So if you are through lithium ion battery technology, if you want to store energy equivalent to 1 liter of fossil fuel, let's say you are expending 1 liter of fossil fuel and getting energy, that much of energy you want to store in lithium ion batteries. Okay, but how much of fossil fuel you are expending? 300 liters. Is this a good technology? Is it a good engineering solution? Definitely not. Okay, and I'm not saying this. The MIT has brought out the statistics, and I have given the links for details. You can, I will leave this anyhow. You'll have this presentation, so you can check for yourself the details of such things. But are we bothered? Are the humans, most of the humans, bothered about these things? No. These things are not known to these things are known to the people who pray, who advocate for good environment and all. Only handful of people know it. The manufacturers, will the manufacturers tell? No, they don't tell. The researchers tell? They don't tell what they are doing. They hide all that. They obscure all those facts and only say that, yeah, this is an efficient lithium-ion battery with so much of energy density. This is an excellent device, and so on and so forth. Now, not just the lithium, you see so many other materials. If you consider India, the ones in the black are available in India, but rest of them are not available in India. And without them, India cannot manufacture their own lithium ion. But instead, they should actually go for some other technology rather than depending on uh, other weaker countries and saying that we have green batteries, we have EV cars, and so on and so forth. Now, okay, these things I have. Okay, another is the EV cars. Okay, now we only think about lithium ion batteries, but what about the how the car moves? The energy, the electrical energy has to be converted into mechanical energy. So you need a motor setup, a motor and stator, right? And they you want a good motor and starter, you need permanent magnets. So if I'm talking about an excellent top-notch EV car, around 10 kilograms of permanent magnets are needed, that too in a particular shape. Do we get these magnetic materials sitting in India? Okay, and if I'm talking about if I'm talking about if I'm talking about let's say India, let's say a second rated EV, okay, at least 5 kilograms of each EV needs 5 kilograms of permanent magnet. Do we have? We don't have. Okay, it's not just the lithium, cobalt and nickel. It is also about the associated material. Once we have all these batteries, okay, and after 10 years they stop working, okay, they are dead. What do you do with them? You need to recycle them. Do we have recycling technologies? No. And some countries in Europe will introduce any technology into the public only if recycling technology is already robust and it's there in place. Otherwise, they'll not introduce the technology. First, the recycling technology, then the technology. Okay, but unfortunately, the philosophies of different countries are different. Some of the countries don't want lithium ion battery technology because they think that human exploitation is there, human rights violation is there. For that reason, they don't want lithium ion battery technology in their country. They'll say we are fine with whatever technologies we have, whatever local technologies we have, we are fine with them. We don't want technologies that actually are through the exploitation of humans and women and other children elsewhere. Now, the related to the FDP, hydrogen energy, okay, green hydrogen energy, and most of you might be knowing 90% of the total hydrogen produced in the world is, okay, and it is not new, it is there for a long time, and that is called as gray hydrogen. I think most of you might be knowing. There is another hydrogen called blue hydrogen, in which, of course, it is better than gray hydrogen, but still there is a large carbon footprint. Now, when we say blue hydrogen, still the non-renewable energies are used in producing this blue hydrogen, but the emissions, there is a mixture of non-renewable and renewable, and the emissions are less in comparison to the gray hydrogen, but gray hydrogen production, but still there is a large carbon footprint. Okay, now why we governments are saying green hydrogen and propagating as if things are going to revolutionize and all. But if you see the Bloomberg news articles, we need a humongous amount. The hydrogen, when we say we want to tap hydrogen as a fuel for whatever reasons, you need humongous amount of hydrogen, and to have that amount, you need to convert humongous amount of energy from renewable only then we will be aligning with even the acceptable definition of green hydrogen. Otherwise, it is at the maximum blue hydrogen, nothing else. Okay, but for that to happen, we need excellent electrolyzers. And electrolyzers, for example, working, the feed can be a seawater, for example. Okay, you need to do bulk hydrolysis. Okay, and that too using renewable energy. Now, do we have that? And many researchers don't even know the difference between electrolyzer and a fuel cell. Okay, unfortunately. Okay, so when we want to produce hydrogen, it is the electrolyzer, and hydrogen is a feed to as a fuel to the fuel cell. Okay, now we need to do bulk hydrolysis. That's a big gap actually, and the amount of hydrogen we are talking about is as I said, humongous. You can check this Bloomberg NEF for details of that. And is there a demand? Is there a demand? Are the villagers, most of the villagers who cook, do you think they will use hydrogen for cooking? Because the calorific value, they will in fact forget about cooking. The amount of energy that is when you burn hydrogen, let's say through piped hydrogen, it will actually cook the vessels, not the food in the vessels. Okay, demand, we don't know what is the demand. Do we need hydrogen? I don't know really if I need to have a supply of hydrogen to my house or something like that, or cars, or I don't know. I've never thought about whether it is. So there is a demand supply relation which is absolutely poor. When government doesn't know what is the requirement, they don't calculate. Nobody calculates. Is it first of all required in the present scenario? If it is required, how much it is required? What are the safety? Do the public, is there a public acceptance? Is there a need analysis is done? Do the public, did you take care, did you bring in public, did you include the public in planning a green hydrogen project? No. So you are violating equity. Okay, now, and when we do research, let's say related to these areas in our lab, it is high time that we should be working at the system level. But most of the researchers in India, across India, work on small things, not on the design, not on the bigger systems, not on the system level. They work on catalysts, they work on improving something, and the advancement is incremental. You may still get a paper, you may still get an excellent public, you may get promotions using that, but is it helpful to the economy? Is it helpful to the environment? Is it taking care of the equity? Unfortunately, as of now, no. Now, when talking about the processing of materials, because as I said in the previously, you need materials with whatever you do, including green hydrogen. For example, you need catalysts. Okay, now many people claim in India that my process is green just because they've used some reducing agent, which is probably a plant extract or naturally available material. Okay, now you see here there is an example. The project is to make 1 kilogram of gold nanoparticles, and you see here there is something called E factor, a simple factor which is actually a sustainability descriptor in related to processing of nanoparticles. Okay, now there are several works. You see gold, I'm just taking gold nanoparticle, the first one, uh, and calculated the E factor for all of them. Not me, somebody has calculated. The nature of the work is like that. And the E factor, for example, the second one from on the extreme right, you have 99,400 and 29,600. Okay, now how is it made? The synthesis reduction with starch and glucose. Okay, starch and glucose are biomolecules, safe molecules, and green. Many tag them as glucose is green. Okay, let me use glucose as a reducing agent. Let me use starch, which is from a natural resource. Any starch from any root, for example. Okay, now you see the waste generated there. If I am producing 1 kilogram of gold nanoparticles by which is a green reagent, namingly, I mean, it's not really green actually. If you see, that process actually generates for 1 kilogram of gold, and that to gold from a gold salt only, not from a gold containing natural resource. Okay, it generates almost 30,000 kilograms of waste. Do you call that as sustainable? Do you call that as green? The same is with other things. Okay, you see such sometimes even the chemical process, the regular chemical process is far more efficient environment wise, economy wise, and equity wise. You don't produce so much of waste, disturb the people in the society, the environment, and other entities in the environment, and spend a lot of money. Spend 1,000 rupees to get 10 rupees, something like that. Okay, but that's how people are. They claim, they exaggerate the results and show, because the reducing agent is glucose, I was able to reduce a gold salt with glucose, and I could produce gold, but you don't talk about the waste you generated. Okay, so that's one factor. That's one E factor. Is as simple. You take mass of the waste generated of the product. Okay, it's the ratio. It is a very well researched factor, which is now a sustainability descriptor. Okay, when you are doing a chemical process in producing some catalysts, find out what is the waste produced in kilograms, and what is the mass of the product you actually, the catalyst you produced in, by considering different chemicals. And that's a simple, very simple sustainability descriptor. You can calculate and find out what is the waste generated per kilogram of the catalyst you are generating. Then you would stop, many of us would stop claiming our process to be clean, green, and whatever, sustainable. Okay, now, not at all this process of it is just exaggerated. If you go into the details and check the quantified parameters, quantified descriptors, you will find actually quite opposite. Okay, okay, the same another process here. There is a work where they have considered 13 green reducing agents, the so-called green reducing agents, and found that the process is absolutely inefficient. And actually, the regular process where the with the we write, right, the hazardous chemicals are replaced with hazardous solvent is replaced with the green solvent. Okay, but actually the so-called hazardous chemical is better when you consider the overall picture than the so-called green reducing agent. Okay, and such things we have to be careful, and we should not wrongly claim that the process is green. Okay, now why do we do why the greenwashing happens? Okay, that's very important. It's basically, it comes down, not everyone understands or wants to understand the overall scenario. They are worried. They have woven their own shell, and they are working in their own shell. Their motive is to publish in high impact journals, or get fame or get money out of what they are doing, but they are not they don't want the overall scenario. Okay, that's one aspect where, that is why the greenwashing happens. Poor academic and research training, and no subjects cover these in the classroom. We should introduce in as early as possible such things train the students. Otherwise, it is too late. By the time they come to the profession, the students, they don't know all of this. So the training is poor. And of course, peer pressure. Okay, my colleague is publishing. My colleague is progressing. My colleague is getting promotion. I am not. So let me do things in an unethical way. Publish, but but then we end up violating all the principles of green such that peer pressure is another aspect. Okay, research reporting is most of the times hyped, overstated. Most of us, we will see, never a PhD thesis in India has negative results. It will always have a positive result, surprisingly, as if the student gets the results in one go. There is no failure, there is no correction to the process. Only one process, the result is there, results are there, discussion is there. Okay, so that particular work is hyped or overstated. Okay, so we should also we should make sure that we report the negative results. In fact, there are actually journals which invite negative results, so that in the future, because we are saying that we should not spoil the future generations. So if somebody in the future follows our wrong research, they might be wasting their resources, wasting their time, and sometimes it can be also a safety hazard. Okay, and not many work on allied technologies. If I'm working on a particular technology, I stick to that. I don't want to discuss with others, because I think that others will steal my ideas, or they don't know, they are not as experts as me, something like that. Okay, that is prevalent in India. Allied working on catalysts, I should know the entire end to end how the system works. I will not produce catalysts which may not work at the system level. Okay, so I need to know in and out of the technologies that go into, let's say, an electrolyzer in producing hydrogen. Uh, uh, I may still be working on catalysts, okay, for electrolysis, but I should know in and out of everything, the current collectors, the flow plates, the everything you should know. Unless you train yourself in allied technologies, you will not. The progress will be only incremental. That may be limited to a publication at the most, but not the advancement of the technology satisfying all the three E's. Okay, and the last point, neglecting less visible aspects, like for example, exploitation of humans, exploitation of children, exploitation of women, exploitation of natural resources elsewhere. But focus is limited to only salient features. Salient features, lithium ion battery technology is very good. It is green. It is going to change our environment. These are features. But what are the less visible? Because unless somebody tells us that, you see, children in Congo are being used to manually mine cobalt. Okay, we don't know. We don't even read such things. We don't come across such things, because the media, the advertisements are in such a way that it is only about lithium ion battery, not about mostly about the salient features of lithium ion battery, not about the other things, socioeconomic aspects. Okay, now, what are the recommendations? You need to inculcate good research practices. First and foremost, any research you do, especially when it comes to the technology, science or technology, it has to be based on design. You need to report the reality. Let it be a failure, but you report it. Encourage mass and energy balance calculations. First approximation, that should be how much energy is going and how spent, what is it, good, bad process, something like that. Even before we do the experiment, we need to do mass and energy balance calculations. That should be a regular part of research, especially when it comes to developing green or sustainable, or in general any technology. Okay, and then scoreboard based reporting. So if you calculate so and so sustainability descriptors, quantify them in the way they are defined. There are several now resources which actually talk about, which are actually define the sustainability descriptors, or the procedures to calculate them, the procedures to report them, the procedures to understand them, all that. The greater number of descriptors you calculate, better will be your score. So these days, some of the journals, high impact journals, they ask you about certain numbers. Okay, please, when you conducted your research, please tell us about these numbers. So unfortunately, we might think that we have excellent results, but we may fail in the scorecard because we have blatantly violated the environment, the resources wasted, the time spent, which also amounts to resource, right? So such a scorecard based reporting should be encouraged, especially about the sustainability descriptors. And every one of us should consciously link our work to the at least some of the aspects or the sub aspects, sub themes in this sustainability development goals. For example, in our university, it is now mandatory that irrespective of the subject, it can be language, it can be science, it can be technology, you need to write 1 page of a or master thesis, 1 page, one of the first pages about how your work is to which SDG or to which SDGs your work is linked, aligns with. Okay, so we need to make a conscious link. So at our university, we have introduced this. Anyone, irrespective of the subject, the student in correlation, in collaboration with the supervisor, in with the help of the supervisor, should write 1 page on how that work SDG you can align with. Okay, something like that. And when we talk about processing of materials, because materials play an important role in energy technologies, including hydrogen energy technologies, we need to think of flow reactor based and high throughput processing, not just gram scale. And that time is gone now. I mean, of course, the fundamental research is important, but even when somebody does fundamental research, you should always parallelly take help of somebody, some other lab, and find out whether this process can be scaled up flow reactor type processing or not. Otherwise, it is of no use. You will at some stage you will be violating one of the E's related to the technology. Okay, and we need to find out AI ML is, everybody talks about AI and ML, machine learning, and a lot of databases. A lot of research is already generated. There are a lot of AI models which we can use actually to identify unidentified raw materials and other chemicals and make accelerated materials development. So this again, AI and ML means design directed engineering. Okay, that's very important. So otherwise also you would do you should do design directed work. But now when you have softwares, when you have algorithms which can help you, it is better we use efficient algorithms to design our work. Okay, and do experiments on the computer before venturing into the lab and wasting all the resources. And startup culture, you might be knowing, everybody now thinks of having their incubating their own ideas and maturing into startups and then becoming entrepreneurs, which is good, no doubt about that. But that culture should not be limited to to tapping the subsidies the governments give. Okay, so if I, for example, in my university, the we have this sort of culture. The university encourages anybody associated with the university, student, master students, bachelor, BTech student, PhD student, anybody, to incubate their idea. Of course, there will be a team which will actually assess whether about the idea, and if they are successful, the university through their incubation centers gives incentives, gives space, gives initial supporting amount, and a lot of equipmental support, a lot of business plan support, a lot of to bring in investors and all that. But just for the sake of leveraging these things, one should not actually venture into incubating their idea. Okay, so startups should be encouraged to get ranking, for their technology. Otherwise, anybody can start, any process without proper assessment of the sustainability parameters, and they may eat up all the resources, all the subsidized water, subsidized electricity, subsidized whatever the university or the incubator gives or the government gives. And at the end, it may not be useful for the society for which they are actually trying to develop the technology. Okay. And of course, the RRR technologies, reuse, repurpose, those technologies should be an integral part of lab research. Okay, that one key recommendation that I would like to make. And of course, when we talk about technologies, when we say silicon solar technology, the photovoltaics, you always keep on improving the efficiencies. Okay, you don't need to discard the technology while developing new technologies. You still want to improve the efficiency of the existing technologies. Now, manufacturers, should strictly get ranking. They also should calculate the sustainability parameters when they mine. Now, you might have seen NMDC, our governmental organization for mining. They have advertisement responsible mining. Okay, because now in order for them to get permissions, in order for them to sell the mined products to some other country, they have to actually get the ranking. Okay, including the public acceptance. Okay, that is why they put advertisement saying responsible mining. That includes environment, equity, because mine is a natural resource, and we all can claim that resource actually. But okay, so I may be mining in an area where it is nearby there is a habitants, like there are people who are occupying the land nearby. Okay, their acceptance is also needed. I cannot force them to leave their own place and I say I will mine here. Okay, so responsible mining is including mining industries. They should do a responsible mining. They should actually calculate. It's mandatory now. Okay, but the new companies which want to venture into such thing should actually calculate the sustainability parameters related to the technologies they want to bring in. Okay. Of course, there are other several things. Regulations, we should regulations and policies. That is where we countries like India lack a lot, because not many are trained in this. For example, we should make recycling first before bringing a technology. Any recycling aspects of the technology should be the first in the policy. Once the recycling technology is robust, then you bring in the technology. Okay, and you should make the public aware. Cultural awareness and public awareness. Their public acceptance is very important. Even before that need analysis is need, does the local public technology. Okay, that analysis has to be done. That should be a part of regulation and policy. Otherwise, everybody will say, I'm developing a technology which will be useful for you. But they'll have their own arguments to support their claims and all that, and their uses of the technology, the benefits of the technology, by hiding by hiding certain important things around that technology. Okay, so public awareness is very important. It should be a part of the policies and regulations, and otherwise, natural resources can be exploited, people can be exploited, people can be cheated with bringing in wrong technologies, forcing the technologies, painting them with the technologies, and forcing them to use the technologies. If, if I may say, 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 if lithium-ion battery technology for whatever reasons. But if I want to drive a car, maybe in the coming years, I may have to forcibly buy a EV, because the government says in my policy I will not have any cars petrol based or diesel based. End of the matter. Nobody in the country can have, because it is illegal. Okay, but that is forcing lithium ion battery technology on me. Okay, but I don't want personally to because I see personally that there is a lot of exploitation than the exploitation fossil fuels. I'm not saying that there is no exploitation linked to fossil fuel tapping in the nature. There is, but this one is much more than that, according to me. Okay, so these things have to become a part and parcel of the regulations and policies. Okay, thank you so much for listening, and I'm open for any questions and discussion.
Yes, sir. Good
Yeah,
evening, sir. Thank you so much for your insightable and also enlightening the lecture, enlightening the people towards the uh, clean, green, and technology. Clearly define what is the difference
thank
between
you.
the green and the people use the technology, the war technology, by harming to the environment, earth, and all the species. Uh, uh, really very insightful, sir. But my question is it possible
Mm.
to mimic the process of photosynthesis in laboratory?
Yeah, people are trying. I think right now only 10% was 10% efficiency. See, the problem is if you want to replicate whatever nature is doing, everything the nature is doing, it is impossible. See, the knowledge the humans have is so less. The nature, for example, in the chloroplast, the outer shell is just 1 nanometer thick.
Yes, yes,
And
yes, sir.
in, yeah, who has decided that it should be 1 nanometer? The chloroplast should have
That
thylakoids, thylakoids.
God
Yeah,
creation.
yeah, that's a creation. Yeah, that's there in the nature. But yeah,
Yes,
to understand that itself has taken a long time for humans because of their whatever skills they have. So yes, if you can replicate even up to 20%, I don't know. I've taken 10%. Maybe 10% is also not there. Okay, you may solve to produce sugars and procedure to produce food, which can actually address some sort of food security issues and all, but not completely. Okay? But yeah, but to understand the energy conversion, natural energy conversion itself has taken long time. Yeah.
yes, sir. Yes, sir. Definitely. Yeah. Thank you, sir. And one more thing is conversion of waste to energy. For example, bio production of biogas.
Yes.
Is it feasible? And it comes
Yeah.
under
Yeah.
green and
See.
green.
See. Yeah. Yeah. So it is definitely possible, but whether you want to name it green, clean, whatever names you want, you need to quantify. For example, I collect waste. Okay, let's say landfill waste, bio
Uh,
waste. Let's say, okay, uh, and then convert that into biochar. Biochar, the converted biochar is excellent for whatever applications, soil amendment or plant growth, or let's say activated carbon for water purification. Excellent, no doubt. But in producing that biochar, if I am polluting gas, that's not correct. Okay, so I need to introduce in that conversion process wherein I can divert that sine gas into another process, because that gas, hot gas, sine gas, you should not leave it into the environment. That is also energy, a form of energy. Maybe that is why I said circular, the continuous cycle reactors. Okay, so wherein even the byproduct other process, like for example in this case the sine gas, okay, which is a form of energy. We may have to find out a way to use it while we convert a waste into a useful carbonaceous material.
yes, sir. Uh, Thank you, sir. Actually, I'm very likes about your lecture because you were concerned about the environment uh, and all the species around us. And also, I want to connect slowly. I'm build up my network to connect the people working on towards the environment and energy. If
Okay.
possible, if you are permits, I will shortly. I will be contact with.
I lost
And
you. Your voice for a moment was gone, actually. Can you
Sir,
repeat, please?
I want to connect with. So I'm building my network. Those people who are working on environment and energy and materials
Okay.
also. I
Okay.
want to make a contact with you if you
Yeah, yeah,
permit.
sure, sure. Sure, sure. No problem. Sure, sure. You're welcome.
Thank you, sir. Thank
Okay.
you so much. A
Yeah.
wonderful lecture. Very
Yeah.
nice.
Any
Thanks.
other questions, please?
Yes, sir. I think we'll proceed to the next session, sir.
Yeah, I think already we
Participants, if
have
you have
lived.
any questions, please
Yeah.
send to me and we will interact to the sir. Yes, sir. On behalf of the organizing committee and entire institute, extend my sincere gratitude to our esteemed speaker, Dr. VVSS Srikanth, sir, for delivering such a insightful and thoughtful, provoking sessions today. Your expertise and the clear presentation have greatly enriched our understanding. What is the greenwashing and sustainable? It is very inspiring us, sir, with the new prospects. So far, we are thinking about that technology. Green technology means people are now we are understand that most of things are greenwashing only. So due to that, if you suppose
Unfortunately,
generating
yes.
the
Yeah.
nanoparticle and all, we are
Yeah. Yeah.
not maintaining this green and sustainability and all. So you have explained very clearly and making exaggerated or misleading claims about the sustainability in sustainable technology. Like that, we explained very well, sir. And what about the lithium ion battery? So lithium ion battery, most of the people are working, but what is the effects about that? And all you very well explained. And also you explained about that why greenwashing happens and what is that the poor understanding and poor academic and research training some peer pressures and all you explained very well, sir. These are the things. And also what is the final recommendations you have given to the society about that green technologies and all. So, like a startups and make a RRRR, you can extend the RRR like anything, keep improving the efficiency of the existing green technologies like that. And also, you have given some of the new topics to our participants, what we can work and all. So, very insightful talks are this one. I think our participants are greatly benefited. Thank you very much, sir. So, once again, on behalf of the organizing committee members, sir. Thank you,
Yeah,
sir.
thank you. Thank you so much. It is pleasure participating in this. I hope the other talks, I mean, will be useful, and I'm pretty sure it will be a learning experience to all the participants. Thank you so much, Professor Swaminaidu, and also Dr. Bhargavi Rani for inviting me. Thank you all.
Yeah. Thank you, sir. Thank you.
Thank you.
Good night,
I'm
sir.
leaving. Huh? Yeah, good
Yeah, yeah.
night.
Good night, sir. Thank you, sir. Yeah, participants will continue to the next session because time is short for the next session. So I will check with Bhargavi madam.
Yes, sir. Mr. Drumel and Mr. Arora, are you in line? Please
Yeah,
confirm.
hi.
Yes.
Okay.
Yeah, just I will give the short introduction. Sorry for making you waiting because the last session started delayed because of lower number of participants. So that's why it took a little bit extra time. We are sorry for that and just will introduce before starting your session. It is my pleasure to introduce Mr. Drumil Gorgi and Mr. Ekansh Arora, two dynamic young innovators and co-founders of Hydrogen Network India, who are jointly leading today's session on role of academia and industry in hydrogen R&D. Together, they bring a remarkable blend of industrial, academic, design, and engineering expertise and are actively shaping India's emerging hydrogen ecosystem. Mr. Drumil Gorgi is a manufacturing process and design engineer and a hydrogen technologist with deep industry experience in fuel cell, mechanical design, hydrogen system integration, and advanced manufacturing. His background includes significant work at Loop Energy Inc., Canada, where he contributed to fuel cell stack design, GD&T based precision engineering, PFD, PD, P&ID development, and lean manufacturing optimization. He currently serves as a co-founder and director of Hydrogen Network India, where he leads efforts in hydrogen skill development, fuel cell training modules, design of ultralight hydrogen fuel cell power systems, and hydrogen-based microgrid solutions. His contributions reflect strong industry academia collaboration and a commitment to enabling India's transition towards hydrogen powered mobility and decentralized clean energy. And Mr. Ekansh Arora is a chemical process engineer with distinguished academic credentials from the University of British Columbia, where he graduated with distinction and received multiple honors, including the Sherman Chen Scholarship. His research and engineering experience spans fuel cell durability testing, hydrogen safety process optimization, data automation, and techno-economic assessments. He has worked exclusively at AVL Fuel Cell Canada, managing fuel cell test stations, optimizing PEMFC performance, developing automated analysis tools, and performing advanced material diagnostics, all contributing to improved reliability and safety of hydrogen systems. In academia, he has led notable hydrogen projects such as pilot scale methane pyrolysis plant design, techno-economic modeling for hydrogen production, CO2 capture system design, and thermal integration and LCA studies, with several projects featured at UBC for innovation. Together, Mr. Gorgi and Mr. Arora bring strong industry experience across hydrogen mobility, electrolyzers, and fuel cells, deep understanding of R&D, safety, TEA, and system design, proven ability to translate academic research into practical industrial solutions, commitment to advancing hydrogen training, innovation, and entrepreneurship in India. Their combined expertise makes them highly suited to speak on crucial roles that academia, industry, and startups play in accelerating hydrogen research, technology development, and deployment. Please join me in warmly welcoming Mr. Drumil Gorgi and Mr. Ekan Sharora to deliver today's session. I think participants will be most benefited as they are from Hydrogen Network India and industry. So please also interact with with them after the talk. Yeah, you may proceed with the presentation, Mr. Gorgi.
Can you see my screen?
Yeah,
Yes, sir.
Okay, thank you so much, Dr. Bhargavi, for the warm introduction, and a very good evening to all the esteemed faculty members, researchers, and students joining us today. We're truly honored to be here, and we sincerely appreciate NIT Raipur for hosting this session and giving us the opportunity to speak with such a distinguished academic community. Uh, we're excited to discuss the role of academia and industry in accelerating hydrogen R&D. And we hope this session sparks new ideas, collaborations, and pathways for innovation. So, our topic for today is the role of academia industry in hydrogen R&D in India, driving innovation, collaboration, and commercialization for a green hydrogen future. So, this is an extremely important topic and timely theme because India's hydrogen journey cannot move forward without strong collaboration across universities, research institutions, industrial partners, and innovators. And in this session, we will explore how academic research, industry driven development, and entrepreneurial initiatives are collectively accelerating hydrogen technologies in India. We will discuss how policies, R&D programs, and national missions have opened new pathways for innovation and how institutes like NIT Raipur can position themselves at the forefront of this transformation. So, our goal today is to help you understand where the opportunities lie in research, in funding, in industrial partnership, in skill development, and in emerging hydrogen technologies that are ready for academic industrial collaboration. So, with that, let us begin our deep dive into how academia and industry together can drive India's green hydrogen future. So, I just quickly like to walk you through the key objectives of today's session. Our focus is to give you a clear understanding of how green hydrogen R&D landscape is evolving in India. So first we look at major R&D policies, schemes, and national programs under the National Green Hydrogen Mission and related government bodies. Then we'll map out the current research ecosystem, the roles of academia, national labs, startups, and industry, and how they contribute to innovation in green hydrogen technologies. Then we'll explore emerging research opportunities, including high impact areas such as advanced materials, electrolyzer innovation, hydrogen storage, safety engineering, and waste to hydrogen pathways. And from there, we'll move into one of the most important aspects for any researcher, pathways to fundraise. And then we look at government grants, international collaborations, corporate R&D partnerships, and industry-driven funding models for hydrogen research. And finally, we'll discuss strategic opportunities for NIT Raipur, where the institute can play a leading role, the kind of projects that can be initiated, and how faculty and students can directly engage with India's hydrogen future. We already did the introduction, so I'll just skip this for now. So, yeah, now let's take a look at government's major schemes and programs that directly support green hydrogen R&D in India. So this is important because funding, mission alignment, and policy direction determine how quickly innovation can move from academia to industry. So we have the National Green Hydrogen Mission, where under the National Green Hydrogen Mission, the government of India has allocated a total outlay of 19,744 crores for the period 2023 to 2030. Within this, there is a dedicated R&D budget of 400 crores specifically targeted at technology development, innovation, and ingenious capability building. Additionally, for financial year 2024-2025, the government has assigned roughly 600 crores in annual kickstart funding to accelerate early stage hydrogen research and pilot development. And then we have the key R&D programs and instruments. So the first major mechanism in this R&D scheme under NGHM is where MNRE issued a call for proposals on 15th March 2024, followed by a second call on 14th July with a deadline of 15 September 2025. These calls focus on accelerating indigenous technologies, lowering costs, and enabling India's led breakthroughs. And then the second instrument is the Strategic Hydrogen Innovation Partnership, or SHIP. This is a public-private platform for mission-oriented research. SHIP is designed to support high-impact collaborative R&D, including pilot demonstrations and commercialization-ready technologies. And then we have the site incentive program, which many of you may already be familiar with. Although site is primarily focused on electrolyzer manufacturing and scale up, it complements the R&D ecosystem by creating a pathway for technologies developed in the lab to reach commercial deployment. And finally, we have the priority R&D areas as defined by the government. So the government clearly defined uh, identified priority research areas. Those include advanced electrolyzer technologies such as AEM, PEM, SOEC, as well as catalytic materials, membranes, stack components, and methods to improve system efficiency. Hydrogen storage is another major focus, covering metal hydride, LOHCs, solid state storage, and high pressure compressed systems. There is a strong emphasis on safety, transport standards, and certification frameworks, which we'll get into later in this presentation. And then we have power to X technologies, such as hydrogen to ammonia, methanol, and other e-fuels, are also key areas, especially for industrial scale pilots. And finally, electrolyzer integration has become critical, and combining renewables with electrolyzers and developing advanced control strategies and enabling grid stability. And together, these programs create one of the strongest R&D support ecosystem that India has ever built for an emerging clean energy technology. And this is the right time for academic institutions like NIT Raipur to tap into these schemes and play a leading role in hydrogen innovation. So, India is standing at a remarkable crossroads in its energy journey as one of the fastest growing economies in the world. Our energy demand is expected to more than double by 2040. And to meet this demand without compromising our climate commitments, we need solutions that are both sustainable and scalable. And this is where hydrogen becomes a game changer. So, hydrogen is often called the fuel of the future, but for India, it's quickly becoming the fuel of the present. And with the National Green Hydrogen Mission, the government of India has committed an investment of 19,744 crores, as mentioned before, targeting 5 million tons per annum of green hydrogen production by 2030. That's not just a policy goal, it's a national movement towards cleaner mobility, decarbonized industry, and energy independence. Hydrogen has the unique ability to store renewable energy, replace fossil fuels in industries like steel and refining, and power heavy vehicles and ships that are hard to electrify. However, achieving this vision isn't just about scaling up production, it's about innovation. And hydrogen technologies, whether it's electrolyzers, fuel cells, storage system, or safety mechanisms, are still evolving. We need continuous research and development to make them more efficient, durable, and affordable. And that's where collaboration becomes essential. Academia brings deep scientific expertise such as new catalysts, membranes, different simulation models, and then the industry brings the ability to manufacture, scale, and commercialize those technologies. And the government provides framework, funding, and long term policy support. And with these three, when these three come together, uh, they form what we call the triple helix of innovation. And it's the helix that truly powers hydrogen revolution in India. Now let's take a closer look at the major hydrogen schemes that the government of India has launched to accelerate manufacturing, R&D, innovation, and commercialization in the green hydrogen sector. So the first and the largest scheme under the National Green Hydrogen Mission is the SITE program. With an outlay of 17,490 crore, SITE is designed to boost domestic manufacturing of electrolyzers and scale up green hydrogen production. The goal is to build India's core manufacturing capacity so that our hydrogen ecosystem is competitive globally. Next, we have the pilot project scheme. So, alongside manufacturing, the government has allocated 1,466 crores specifically for pilot projects. These focus on real world demonstration in steel, shipping, mobility, and emerging applications. These pilots are extremely important because they validate technologies, create market confidence, and accelerate commercial adoption. Next, for research and innovation, the government has earmarked 400 crores under the dedicated R&D scheme. This supports collaborative consortia involving IITs, CSIR labs, national institutions, and industry partners. And so far, 23 projects have been supported. And the second round of calls was issued in July 2025, including opportunities for international collaboration, such as joint proposals with the European Union. Next is the startup support call, recognizing the importance of innovation and entrepreneurship. This mission also includes 100 crore rupees for startup support call, and this provides up to 5 crore per startup for pilots, prototypes, and breakthrough technologies. This is a major opportunity for young innovators entering the hydrogen space. Another significant mechanism is SHIP, the Strategic Hydrogen Innovation Partnership. SHIP acts as national level R&D consortium, bringing together BARC, ISRO, CSIR, IITs, IISCs, industry partners, and startups. The idea is to drive mission-oriented research where academia and industry work together from day one to deliver deployable hydrogen technologies. Next, we have lastly the Hydrogen Research Initiative under DST continues to support advanced research in hydrogen production, storage, distribution, safety, and novel applications through its hydrogen and fuel cell program. This scheme plays a crucial role in building long-term scientific capability and supporting fundamental research. And since we're talking about so much investment, uh, to understand the scale of India's ambition, let's break down what it actually takes to produce 5 million tons of green hydrogen per year, which is the goal by 2030. So, this target sits at the core of the National Green Hydrogen Mission, and infrastructure needed is enormous. So, this mission aims for 5 million tons per annum of green hydrogen, and the associated electricity requirement is on the scale of what this entire countries consume. So, producing 5 million tons per annum of hydrogen requires about 250 terawatt hour of electricity per year, which converts into a continuous power demand of 28.5 gigawatt operating 24/7. And if we rely on solar energy to get all the electricity we need to power the electrolyzers we would need 114 gigawatt of dedicated solar capacity, roughly 254 million solar panels, 450 watt each, with a surface area of about 558 kilometers square just in panel surface area. But if we include the spacing, shading inverters, and all the infrastructure that goes with it, it comes up to be about 1100 to 1400 kilometers square, which is 340,000 acres, which is the size of Delhi NCR or two times the size of Mumbai. And then if we talk about the electrolyzer requirements, we need to continuously operate at 28.5 gigawatt and 2,854 plants of 10 megawatt each for 24/7 renewable supply. However, if we operate only on solar, which runs at 25% utilization, we would need 11,416 plants of 10 megawatt each. And to put this into perspective, the image on the right is Gale's new 10 megawatt green hydrogen plant, one of the largest operational units in India right now. And using this as a reference point, achieving 5 megaton per annum would require about 2,854 Gale-sized plants if they run continuously using renewable energy, and around 11,416 Gale-sized plants if they run only on solar energy. So this comparison illustrates the sheer scale of deployment needed to meet the National Green Hydrogen Mission target. And India will require a solar footprint the size of a major city and thousands of Gale-scale electrolyzer plants, representing one of the largest green hydrogen infrastructures anywhere in the world. So now that we've understood why hydrogen and collaboration are essential, let's take a step back and look at India's hydrogen value chain. from how hydrogen is produced to how it is stored and distributed, and then finally used. So in India, hydrogen production is shifting from gray to green hydrogen, and the National Green Hydrogen Mission envisions scaling up green hydrogen through electrolysis powered by renewables. So companies like NTPC, Reliance, Adani, and Greenco are investing in large-scale electrolysis projects, particularly alkaline and polymer electrolyte membrane systems. We're also exploring biomass gasification and photoelectrochemical splitting, which are still in early research stage. And the next big focus area is indigenization of electrolyzer technology. And that's where academic and industrial R&D partnerships are crucial at the moment. Next, we have storage and distribution. So once the hydrogen is produced, storage and transport become key challenges. And currently, India relies primarily on compressed gas cylinders at high pressure. But for long-term scalability, liquid hydrogen and chemical carriers such as ammonia and methanol are being explored. And then Indian Oil, NTPC, and HPCL are already setting up hydrogen refueling stations and blending pilots in city gas grids. And a long-term vision includes a dedicated hydrogen pipeline network, much like our existing natural gas infrastructure. And then hydrogen has multiple end-use pathways in India. In transport, hydrogen fuel cell buses and trucks are being tested by NTPC and Ashok Leyland. In industry, refineries, steel, and fertilizer plants are preparing to replace grey hydrogen with green. And power generation is emerging as a key use case, blending hydrogen with natural gas for turbines or using it in fuel cell based microgrids for remote areas is also an option. And finally, exports. So, India is positioning itself as the global supplier of green ammonia and hydrogen to countries such as Japan, Korea, and Europe. So, as we can see, hydrogen forms an entire value chain, and every link in that chain, from research to deployment, offers massive scope for innovation. Now, next we look at where academia fits into this ecosystem, the knowledge and research engine driving India's hydrogen revolution. So now we look at the role of academia because universities and research institutions are truly the backbone of India's hydrogen innovation ecosystem. Most of the breakthroughs in materials, electrolyzer performance, fuel cell design, and hydrogen safety originate from academic labs. So the first and most important contribution is fundamental R&D, and institutes like IIT Delhi, IISc Bangalore, and BHEL R&D are driving cutting edge research in catalysts, membranes, bipolar plates, and next generation electrolyzer and fuel cell materials. This early stage scientific work is critical because the performance and cost of green hydrogen technologies depend heavily on material breakthroughs. Then, second, we have academia providing test infrastructure and centers of excellence that are essential for validation of current technology. Facilities such as CSIR, CERSI, IIT Madras, HTIC, and the test beds at IIT Bombay offer advanced characterization tools, fuel cells, and electrolyzer testing rigs, and reliability evaluation platforms. These are the places where prototypes are tested, performance is measured, and industry technologies are verified. And third, academic institutions play a major role in skill development. So we have IITs, IIScs, NPTEL, and other institutes now offer hydrogen technology courses, modeling workshops, simulation training, and even hands-on demonstration kits. This is crucial for building the workforce that India needs: engineers, researchers, technicians, and faculty trained specifically in hydrogen. And finally, academia acts as a launchpad for innovation. Programs under DST, MNRE, and SERB support university-based startups, research consortia, and deep tech innovation in hydrogen production, storage, safety, and mobility. Many of India's hydrogen startups today were incubated within IITs and NITs, benefiting from mentorship, lab infrastructure, and early investment. So, academia is not just about contributing to hydrogen research, it is enabling the entire ecosystem from fundamental science and talent development to testing, incubation, and industry partnerships. So, one of the most important roles of academia in the hydrogen ecosystem is conducting deep fundamental research, the kind of science that directly determines the cost, efficiency, and scalability of hydrogen technologies. So, a major reason hydrogen stacks are expensive today is the use of the rare and costly elements in membranes and catalysts, materials like platinum, iridium, and rhodium. Academic research in materials science is essential for developing alternate catalysts, lower loading membranes, and novel coatings. And these innovations can dramatically reduce the capital cost of fuel cells and electrolyzers. Next, we have process innovation. So, academia also drives process level innovations, simplifying chemical synthesis routes, improving reaction workflows, and reducing the number of processing steps. Better process engineering leads directly to higher manufacturability, greater consistency, and lower production costs. And today, electrolysis is still an inefficient process, and nearly 60% of the input energy is lost across electrolysis, water purification, compression, drying, and storage. So, academic research is crucial to improve water treatment efficiency, membrane hydration control, compression and storage technologies, and overall system integration efficiency. So, incremental improvements in each of these areas collectively result in a much higher hydrogen yield and significantly lower operational costs. So, next we have some emerging research scope where one exciting area of research is direct seawater electrolysis, which has gained significant attention due to India's massive projected water demand for hydrogen production. So, why do we need direct seawater electrolysis? So, by 2030, as um, we discussed before, we need to produce 45 million cubic meters of demineralized water to meet the green hydrogen targets. And producing and transporting this purified water leads to energy losses, higher operational costs, and pressure on freshwater resources. So, this is why researchers are exploring ways to use seawater directly as feedstock without passing it through conventional reverse osmosis or desalination steps. So, there are two different technology pathways that are being explored right now. The first pathway being inhibitor enhanced alkaline slash AEM electrolysis, where the first pathway is chlorine is being explored is adding a chlorine evolution inhibitor into existing alkaline or AEM electrolyzer systems, and this prevents the formation of chlorine gas at the anode, which is the biggest challenge in seawater electrolysis. So this advantage is that existing electrolyzers can be retrofitted with minimal modification and no desalination would be needed, which means no additional energy penalty, making the process more cost effective. And then we have technology pathway 2, which is directly coupling the electrolyzer with a forward osmosis module. Here, the forward osmosis module pulls water across naturally using osmotic pressure, removing salts and impurities right before the electrolysis step. This reduces scaling, corrosion, and membrane degradation while still avoiding the high energy consumption of large-scale desalination plants. And if both of these pathways show enormous promise, and if successful, both seawater electrolysis could eliminate one of the biggest bottlenecks in green hydrogen production, which is freshwater demand, and make coastal hydrogen hubs for far more sustainable and cost competitive. Another emerging technology is solar water splitting. So this is one of the most exciting emerging pathways for low-cost green hydrogen. And today, most green hydrogen relies on a two-step process. A photovoltaic panel generates electricity, and that electricity then powers an electrolyzer. While effective, this architecture brings two challenges: high capital cost and energy losses during electrical conversion and transmission. So researchers are exploring whether we can combine both steps into one device. That's where uh, solar water splitting or PEC hydrogen production aims to do. Instead of using photovoltaic plus an electrolyzer, we use specially engineered semiconductor photoelectrodes that directly absorb sunlight and split water. So this integrated approach offers several advantages, such as a simplified system, fewer conversion losses, and the possibility of significantly lower cost green hydrogen production. It also fits perfectly with India's strengths, which is abundant sunlight and a need for decentralized hydrogen production. This image on the right shows a typical multi-layer photoelectrochemical structure where tin oxide, silicon, and NiO2, each layer performing a different function. When sunlight hits this stack, electrons and holes are generated, and electrons move towards the hydrogen evolution site, while holes drive oxygen evolution. In other words, the device converts sunlight directly into hydrogen without needing an external power supply. Although still in research stages, photoelectrochemical water splitting is a promising direction for next generation hydrogen technologies. Another key emerging research area is the development of advanced hydrogen carrier fluids, especially as India looks to scale exports and long distance hydrogen transport. Today, ammonia is the most widely used hydrogen carrier because it is energy dense and easy to transport internationally. However, ammonia is also highly toxic, corrosive, and difficult to handle, which makes large-scale logistics and safety management extremely challenging. So, a promising direction is the conversion of hydrogen into reversible organic carrier fluids, often known as LOHCs, liquid organic hydrogen carriers. These are stable organic liquids that chemically bind hydrogen and release it on demand. So the major advantage is that these carrier fluids can be transported and stored just like conventional fuels using existing pipelines, tankers, and fuel infrastructure. And this makes hydrogen logistics simpler, safer, and far more cost effective. And for India, this could significantly boost hydrogen exports, and for industries operating in remote regions, LOHCs could serve as efficient captive hydrogen solutions without the need for high pressure storage or cryogenic systems, which require a lot of energy. And then overall, organic hydrogen carrier fluids represent a major opportunity, improving safety, reducing handling costs, and enabling true large scale hydrogen mobility and trade. And then let's look at a very promising solid state hydrogen storage method, which is metal hydrides. So, metal hydrides store hydrogen by chemically absorbing it into the lattice of a metal or alloy. When hydrogen gas comes in contact with certain metals, it gets reversibly absorbed, forming a metal hydride compound. And to release the hydrogen, you simply add controlled heat, and the hydride decomposes back into the metal and the hydrogen gas. We're essentially storing hydrogen in solid form, which makes it much safer and much more compact than pressurized gas tanks. So let's talk about the materials that are used. So alloys like lanthanum nickel 5 and titanium iron alloy are already used commercially, and they absorb hydrogen at low pressure, around 1 to 10 bar, and are quite stable, though they store only about 1 to 2 weight% of hydrogen. And on the higher capacity end, we have materials like magnesium hydride and sodium alunate, which can store up to 7.6 weight%, but they require temperatures of about 250 to 300 degrees Celsius to release the hydrogen. Researchers are also exploring complex hydrides like borohydrides and alunates, which have even greater capacity, but they're still in early R&D. If we compare metal hydrides with high pressure gas storage, volumetrically they are far superior since they can store up to 120 kilograms of hydrogen per cubic meter, which is nearly 3 times what a 700 bar tank can store. But gravimetrically, they fall short, and these systems are very heavy, and the hydrogen to total mass ratio is low since the tank is metal and we have a lot of metal powder inside the tank, as you can see in the image on the right. But they're also very safe, operating at low pressures with hydrogen chemically bound in the solid matrix. So the main challenges are weight, cost, and thermal management, because these materials are heavy and they need heating and cooling to function efficiently. They're best suited for stationary applications like backup power systems or renewable energy integration, where space and weight are less of a constraint. Some specialized mobile use cases are submarines, military drones, or off-grid hydrogen vehicles that have already tested hydride tanks, but widespread vehicle adoption still faces hurdles. So, in summary, metal hydrides offer excellent safety and high volumetric density, but improvements in weight and thermal efficiency are key to unlocking broader applications.
Thank you, Ekansh. I would love to carry on uh, with the remainder of this presentation. So I understand we are a bit short on time, so I will try to wrap this up as soon as possible without omitting a lot of information. Starting with the role of academia with testing infrastructure. So in September of this year, Ekansh and I actually visited the first R&D conference in Delhi, specifically dedicated to the hydrogen economy of India. And what came up repeatedly was the lack of testing infrastructure in India and the primary bottleneck for developing new kinds of technologies. And because, as we know, to test field viability or to go from TRL 3 and 4 all the way to TRL 6, 7 or to commercial readiness, we need testing infrastructure. So talking a little bit about what testing infrastructure in the hydrogen economy entails, starting with performance testing, both for electrolyzers and fuel cells. This involves measuring hydrogen output per kilowatt hour, including the stack efficiency, polarization curves, IV characteristics, and degradation behavior. Most commercial electrolyzers operate at 55 to 65% efficiencies. And evaluating improvements requires precise sensors, water purification systems, and pressure regulation. Then comes durability testing. This is critical because degradation directly affects the cost of an electrolyzer stack. Um, this is mainly caused by hydrogen embrittlement or due to because hydrogen needs to be very pure. There are certain particles in hydrogen that can degrade electrodes and the membranes of an electrolyzer, which is why long duration cycling tests of over 1000 plus hours is industry norm when it comes to identifying failure modes. So such tests are essential for R&D grants and getting that industrial validation. Then we come to adaptability of variable renewable energy. So India's hydrogen will predominantly be renewable energy based, which is the goal. That means electrolyzers must be compatible with fluctuating solar and wind input. And in order to test this, we require programmable power solutions. So simulating different kinds of loads and advanced controllers, institutions need to be capable of running such natural simulations and identify the natural loading and the natural real world scenarios. And finally, we have purity testing. So fuel cell grade hydrogen must meet specific ISO standards. ISO standards such as 14687. This will require specialized again systems and testing infrastructure such as gas chromatography, impurity detectors, and sensors to detect moisture, oxygen, and all the variables associated with system efficiency. Can we go on the next slide? Okay. So now talking about how central and government labs and even other private research institutes such as IIT um, set up test facilities, and how do you actually get funding for such testing facilities? So facilities can be a great way for a university to actually um, be actively involved in R&D with green hydrogen. So in terms of collaborating with new startups, industry players, and having that testing infrastructure will really help them sort of be a part of the development process, and also in that way build expertise for future developments and future projects. So it is a win-win situation. So here we have prepared, based on the National Green Hydrogen Mission, certain guidelines were given on do what does a funding proposal look like when applying to build a test facility. Starting with the technical scope, you need to have facility maps of the green hydrogen value chain. So clear list of tests, what kind of equipment is required, and what kind of tests would be carried out, all following international standards. So much of these standards can be found online with a little bit of research. And what can be done is to loop in other international universities where the hydrogen R&D value chain is strong, such as Germany or Korea. Safety is another very, very important factor. So a safety management plan needs to be a part of the proposal. And moving on to the execution plan, uh, detailed capex and installation plan within 12 to 18 months timeline is required. So what would be an estimated capital expenditure that the university is looking at? Again, implementation responsibility assigned to an executing agency needs to be assigned. All regulatory approvals need to be identified. Environment, again, emphasis on safety is required. How would those test systems would be commissioned? Okay, would the vendor themselves would be coming in? Would they be training the faculty to install the test machines? Everything needs to be a part of the funding proposal. Next, we have accessing model and financials. Each testing facility needs to be open for use to industry professionals and academia both. So if there is another university that would like to basically use the testing facilities that you are planning to set up, uh, they should be allowed to do so, and that is a key factor in availing funding for such campuses. The the operational expenditure of your requirement cannot uh, exceed 15% of the total grant that is given by the government, that is planned to be given by the government in a span of over 4 years. In case of co-funding, so let's say there is another university that wants to go in, that NIT would like to collaborate with or co-fund a research facility with, that model needs to be clearly defined. Finally, we have outcome and deliverables. So what kind of, again, parameters would be tested and how would data be collected? What is the quality control of the data? How the robustness of the data be tested? So those sort of details need to be part of a test facility funding proposal in the hydrogen economy. Next slide. Now we talk about skill development and knowledge. So one of the fundamental roles of an academic institution is to uh, develop skills within the faculty and also the student body, that to uh, state of the state of the art with state of the art you know, talent and skill development. So what we normally
Sir,
say
your voice is breaking, sir.
okay. Now Yeah, am I audible now?
Yeah, yes, sir. Please proceed.
Yes?
Yeah,
Okay,
please proceed.
awesome. Great. I'll just wait for Ekant to screen sharing. Okay, great. Yes. So as I was saying, importance to simulation softwares. There are a lot of simulation softwares available in the market. What simulation softwares allow us to do is this rapid iteration of designs and to not get 100% representations of how it will perform in the real world, but you can test different materials, different designs, and the effect of variables such as heat and physical sort of forces and stresses on every design before you can actually get it fabricated or prototyped in the real world. This significantly cuts costs and the risk by reducing repeated physical testing. We can go to the next slide. Okay. So here is a quick summary of the industry simulation softwares that are available and have been used to make developments in the hydrogen value chain. So, for instance, we have the Aspen HYSYS, where a university in Brunei used Aspen HYSYS to simulate hydrogen production from plastic waste. So, this was a techno-economic assessment. Then we have a university in South Korea, which is a leader in hydrogen development and R&D using COMSOL multiphysics, a 3D modeling software that help them model the water electrolysis in a PEM based cell. This included the flow simulation and also the electrochemistry, so where you can vary parameters such as the voltage, the current, the power. Then ANSYS being one of the most popular softwares globally for end-to-end simulation requirements. So you have China using Fluent-based CFD study on hydrogen leakage and explosion behavior in fuel cell buses. So hydrogen leakage and explosion is something that is even dangerous to test in the real world. So this is where you see how the power of simulation softwares can really help a university or even um, a student that learns how to use a simulation software can be great contributors to the industry once they pass out and go into the real world and find a job in the hydrogen sector. Then we also have a Siemens, a software by Siemens. A lot of emerging universities and even companies in India are beginning to use the Siemens SimScape software, helping them model their hydrogen electrolyzer operations and to even test the robustness of their system under different conditions. Next slide. Now we can talk a little bit about hands-on training and the hands-on skill development. So handling hydrogen is something that a lot of universities are not exposed to, the student body or even the faculty. So in-house hydrogen skill development or the creation of hydrogen labs is something that the government is really pushing for at the moment. They would like students to understand how hydrogen is made from electrolyzers and how fuel cells can use hydrogen to create electricity. How this can there is understanding of instrumentation. There is the know-how of using gas flow controllers or sensors, and what kind of tests do industry players run in this sector when dealing with their own hydrogen electrolyzers and fuel cells. So there are such hydrogen educational and lab kits that can be installed at universities to run lab demonstrations and lab experiment programs with students, with faculty, and it sort of just complements the entire R&D workflow. Also gives students a stronger placement opportunity at emerging local hydrogen economies. You can also run capstones and build capstone projects around lab setups and test hydrogen, the robustness of any system that is being designed or tested. Okay, next slide. Now, the next and final step that we have in the role of academia is startup incubation. As Ekansh also initially mentioned during at the beginning of this presentation, that the government is really looking forward to new hydrogen related startups to come up and deploy, at least at right now at the pilot scale, deploy their solutions in the market. So there are certain ways that universities are going about this process. So, for example, IIT Delhi has been running the Foundation for Innovation and Technology Transfer, which is the FITT. So what they have achieved to do is they have developed a technology transfer ecosystem where and an incubation program that is a closed loop system in itself. So there is the flow of this of such a program follows a 6 to 7 step process where a PhD or a postdoc researcher first develops a breakthrough technology. That technology is demonstrated at the lab scale, which is your TRL 3 to 4. After that, we have a research team forming a startup company, or an existing industry partner comes in and collaborates with the research team to incubate a startup within the university. So this sort of turns your researcher into a CTO, Chief Technology Officer of the newly formed startup. And this is a very strong prevailing culture in a lot of R&D institutes. After that, a equity model is created where the university, the research team, the partnering industry player all benefit from an equity model. They get lab access, seed funding from the government, from the university itself, and that sort of any revenue generated from that is fed back to the university. So it creates this win-win situation for all parties involved. Another such initiative is the ATAL Incubation Center, a flagship initiative, and it is an umbrella structure that has been mandated to promote innovation and revolutionize the entrepreneurial ecosystem in the country. So they give a grant of up to 10 rupees, 10 crores for a maximum period of 5 years for setup and infrastructure. IIT Raipur is a member institute of the ATAL Innovation Mission. Okay, next slide. So this is a brief map and a process flow diagram of sorts of how academia and industry collaboration works. We have the apex policy and funding layer, then the central research organizations such as the CSIR. The map on the right is a map of all the CSIR central research institutes working on different domains in India. Then we have the academic and R&D institutes, we are IITs and NITs, and then we have the technology transfer offices. So now what is happening is these technology transfer offices, a lot of times are now being integrated with the academic institutions itself, so that there is a better commercialization process of any technology that is, or any breakthrough that is created in a university. A lot of times good breakthroughs are take very long time to become commercialized. So this is a um, emerging trend and should be really considered as a part to efficient commercialization of hydrogen, green hydrogen technologies. Next slide. Now, again, this is another representation of in a very specific green hydrogen context of how the institutions or the country's resources flow when it comes to green hydrogen R&D. So the Ministry of Renewable Energy leads the green hydrogen mission, and they operate their schemes such as the R&D scheme or the startup pilot scheme, project schemes. So that is your tier one layer of the resource framework. Then we have the tier two resource framework, which is the centrally funded research labs. So these are all your CSIR institutes with very specific domain expertise. Um, what is good about these facilities is that they have a pre-existing access to government funding, and they tend to create these centers of excellence in the hydrogen space. There are still not many of them that have hydrogen infrastructure or hydrogen research infrastructure, but how they are positioned in a way to collaborate with other research institutes, and they actually invite other research institutes to utilize their facilities, um, so that uh, development and breakthroughs can be fast tracked in the country. And then there is the tier three sort of resource framework, which is one of the most important, which is NITs and the IITs, that as innovation engines. Academic institutes, they function as both knowledge generators and also commercialization enablers. They are the ones directly talking to the local industry, and they enable a structured dual track approach, where track one is fundamental and applied research, but they also are the ones who carry out the field tests and the prototyping, and basically getting that final proof of concept before full scale commercialization. Next slide. So now, how do you deploy a breakthrough in industry? Okay, let's say, I think even our previous speaker mentioned that a lot of times breakthroughs in the lab are not deployed in the industries successfully. And this slide sort of stresses on why industry deployment or partnering or collaborating with industry is so important. So the first path to do so is direct industry sponsored research. So an example of that is a company, Omium International, which is a foreign company, collaborated with a CSIR institute for developing advanced materials in PEM electrolysis. So they directly fund this research at our research institutes and address very specific technical challenges. And the next thing we have is consortium-based R&D. So this is where the SHIP, Strategic Hydrogen Innovation Partnership, sort of sits. Here, government institutes and central labs, plus our research institutes such as an NIT Raipur and an industry partner, all three come together to form a consortium and collaborate on multi-year projects. So this really brings that scale of deployment, and ensures a smooth flow of funds, and national level infrastructure is leveraged, because you have all three parties: the policymaker, the innovator, and the executing commercialization partner. being a part of this of a consortium. The third one is a joint development agreement. So similar to consortium based, but again more focused on MNC, or in this case, multiple universities and research institutions come together to co-develop technologies instead of uh, the research partner or a industry partner coming and giving them a project or a project sort of goal. So an example of this is how L&T and IIT Bombay collaborated to scale up commercialization and manufacturing of their electrolyzers, alkaline electrolyzers. Next slide. So now let's talk a little bit about how NIT Raipur can be a strong force in the hydrogen R&D ecosystem. So on the right, you have images of Adani, the Adani organization launching India's first hydrogen-powered mining truck in Chhattisgarh. Mining, steel, and even biohydrogen. So mining and steel directly being benefiting from the hydrogen sector would be mining. In terms of mining, all heavy duty trucks, your construction machinery, your loaders, your excavators, a lot of development happening on retrofitting their engines with hydrogen ignition or hydrogen ICE engines, hydrogen combustion engines. And because of the high energy density in hydrogen, this is increasing in viability. JCB, prominent construction equipment companies, are already working on their hydrogen combustion engine. So in the mining sector, this is very valuable. Then comes steel, direct reduction of steel of coke, and to make steel using hydrogen is going to be super valuable. JSW has already commissioned a plant to start using hydrogen to directly reduce iron ore and produce steel out of it using green hydrogen. So there is a massive decarbonization opportunity over there. Again, a lot of universities tend to collaborate with MNCs or the big sort of pan India companies. In Raipur and Chhattisgarh, there is a good opportunity to collaborate with local industries, the local steel industry, the local farming industry, to basically develop breakthroughs in biohydrogen, bioethanol, and for using hydrogen as a feedstock to decarbonize hard to abate sectors. So this will sort of really, push the limits of regional decarbonization. You have the big companies already, with working on this on their big plants, but regional play is going to be equally important. And deploying solutions in regional clusters, regional industrial clusters, is where strong value is projected. Next slide. So another slide to reinforce optimization of IP management, incubation, and licensing. So as I previously mentioned, incubating startups, using the breakthroughs that are developed in-house within the universities will be super valuable. But to achieve that and to do it right, to achieve that well, you need to manage IP and technology transfer pipelines well. So you revising KPIs, key performance indicators, to give credit to the researchers, to the research team, to give them to coming up with the right equity models for research teams and the university. And these clauses need to be a part of PhD thesis so that in case of research breakthroughs, they can be commercialized well in good faith, and it can create an ecosystem of innovation within the university. So licensing, technology transfers are very important, and because the industry is so emerging, um, there is there is a lot of opportunity to do pilots, to do pilot testing, to basically demonstrate technologies. So it is important to protect the IP and also to optimize its management. Next slide. Again, it is important to leverage collaboration and funding architecture. So the Green Hydrogen Technology Accelerator platform called GHTAP is a membership that is underutilized. It is a platform that provides access to different existing testing facilities, gets you access to industry mentorship and funding connections specifically for hydrogen R&D. So NIT should really look into institutionally joining um, pre-existing hydrogen clusters. We now have hydrogen valleys or hydrogen hubs at Deen Dayal Port in Gujarat. There is one coming up in Pune. There is one coming up in the southern part of India. So um, the Cochin shipyard is also going to be a green hydrogen hub. So leveraging these hydrogen clusters and ecosystems would be a strong strategic opportunity. Next slide. Okay. So just to wrap things up, this was all that we wanted to talk to NIT Raipur about in terms of the importance of R&D, the R&D ecosystem, and the importance of breakthroughs in hydrogen. There is a lot of work to be done, a lot of efficiency gains that can be achieved in systems. But for that, skill development and education remains the primary backbone. So something that Hydrogen Network India does is training workforces in hydrogen, developing industrial SOPs and fire response, providing lab kits for skill developments and building those lab infrastructures. Also giving simulation software training and developing the overall skill set both for students and faculty members across India. And finally, next slide. So finally, we have a webinar in December that will focus on waste to hydrogen pathways for a green future. So we have a renowned speaker and a renowned expert who's also the founder of Revive Clean Tech, Mr. Sanjay Singh. He is from IIT Indore, and he will be talking about waste to hydrogen pathways for a green future. So I will leave this slide on here for anyone interested, and feel free to ask us any questions. That is the end of our presentation. Thank you so much.
Yes, participants, do you have any questions? Yeah, I think there is no questions, but
Awesome.
the topic is very much interested, sir. Yeah, given. So mostly, what is the academic requirements and how we can develop this hydrogen technology? to the academic and academic research and the collaborative, how the collaboration to the industry, especially for hydrogen R&D. So any questions from the participants?
Sir, good evening, sir.
Yeah, please.
Sir, in point of storage of hydrogen, in case of what type of polymer composites can we use? Either synthetic or natural. What type of polymer composites uh, we can uh, we can use for this storage of hydrogen? Can you please explain, sir?
So right now there are for gas-based hydrogen storage, there is type 3 and type 4 cylinders. So normally hydrogen gas storage or any industrial gas storage traditionally was stored in heavy mild steel and steel sort of canisters or cylinders, you may say. And now we have emerging technologies to use carbon fiber and glass fiber to with aluminum liners. So you have aluminum liners and a weave of glass fiber strands with epoxy coating are done around these cylinders. And what uh, has been achieved is a high pressure capacity for that the cylinders can withstand while being just 25 to 30% of the weight. So a glass fiber based composite cylinder would be called type 3, and the most advanced one is now emerging in India called type 4 cylinder for storing hydrogen as a gas. So type 4 cylinder uses carbon fiber as a to basically take an aluminum or any other metal alloy as a liner, and then you have weaving the weaving process that is done around this liner with this material that is coated in epoxy to build a high pressure vessel.
Okay, sir. Thank you, sir. Sir, means can we use fiber filaments or fiber fabrics for the type 4 tanks? And
So for
HDP also, I think we can use it.
I'm not sure about
HDP.
HDP, but for carbon fiber, uh, there are machines that use filaments. In case of specifically in the case of type 4 cylinders, what they do is they use pre-preg fibers to and an automated arm to basically line a cylinder that is rotating on a fixed axis. So what I'll do is I'll just show you a quick video on that or share the link.
Okay. Yes. Thank you very much, sir. Thanks.
Yes, I'll just put that in the chat.
I think right now
It is
mostly they are using the synthetic polymer composites only. The natural fiber composites are not yet tested so far, and a lot of research work is going on in polymer composites, as per my knowledge. Still, these composites use for hydrogen storage is in inception stage. A lot of research work is going on. I
correct.
think people can take up the topics because I am also working in this area for hydrogen storage tanks for aerospace industrial applications. So, so a lot of work is there to be done.
Absolutely.
Yeah. So I think there is no any other questions from the other participants. Yeah. If not any questions, I want to conclude the sessions. On behalf of the organizing committee, the Department of Mechanical Engineering and Metallurgical Material Engineering, NIT Raipur, and all the participants of this ATAL FDP, I extend our heartful gratitude our esteemed speakers, Mr. Drumul and Mr. Akansh, for the delivering an insightful and inspiring expert talk, especially on the role of academic and industry in hydrogen R&D. Sir, your deep expertise and the clear articulations of the emerging opportunities in hydrogen research have truly enriched our understanding. The way you highlighted the collaborative pathways between the academia and industry has opened new directions of our research, faculty, and students. You are also emphasized that what is the opportunities for the NIT Raipur. It is not only NIT Raipur, you have given the example to the NIT Raipur that it may be similar to the any other academic institutions. We sincerely appreciate the time and effort you devoted on this session, and we are gratefully for the acknowledge you have shared with us today. I also extended my thanks to all the participants, faculty members, and organizers for their active engagement and support in making this session a grand success. Once again, thank you, sir, Mr. Drumul and Mr. Akans, for your valuable
Thank you, Dr.
contribution to
Swami.
this FDP.
Thank you, Dr. Swami. Thank you, Dr. Bhargavi, for inviting us to present in front of all the esteemed members of this meeting. Thank you so much.
Yeah, thank you, sir. We will come back to you. We have some more things are there. We are planning. We are
Great.
also developing some of the center of excellence related to the hydrogen R&D. We'll come back to you, sir.
Great, sir. Happy to
Yeah,
help.
thank you so much.
Yeah. Thank
Thank
you, sir.
you.
Thank you.
Have a good night. Thank you. Take care.
So have a good night, sir.
Yeah, have a good night. Thank you.
Yeah, thank you. Yes, participants, you can leave this meeting. So actually, I'm taking the attendance through the meeting only. So you have to enter your name while joining in this meeting. You have to enter your name as exactly about that your registered name. Then we can easily take the attendance. Right? I hope you all people are enjoyed for today's both the sessions, and we'll meet you tomorrow again. Thank you. Good night. Bye bye.
అంతే అలా వద్దే అంతే కింది